recording for page 1, we're going to be looking at integrals of the type integral tangent to a power x, secant to a power x, dx. The identities that we're going to use are the 1 plus tangent squared equals secant squared 1, the rearranged tangent squared equals secant squared minus 1, and that the derivative of tangent is secant squared, and that the derivative of secant is secant tangent. Our first recipe is this. If the power on the secant is an even positive whole number, split off a factor of secant squared and express everything else in terms of the tangent. The simplest example of this sort of thing is integral of tangent to the fourth x, secant to the fourth power x. The thing that I lock in on here is the even whole number positive power on the secant, the 4 in the secant to the fourth power. I'm going to split two factors of secant x off, leaving me with tangent to the fourth x, secant squared x, and the plan is to re-express everything that remains in terms of the tangent only. This will work because the derivative of tangent is secant squared, and I'll be able to do a substitution. Since secant squared of x is 1 plus tangent squared of x, I can rewrite that as the integral of tangent to the fourth multiplied by 1 plus tangent squared times secant squared x dx. Obviously, I'll be able to do a substitution since the derivative of tangent is secant squared. Letting u equal tangent x, du dx is secant squared x, du is secant squared x dx, which is the end of the previous line. The integral becomes integral of u to the fourth times 1 plus u squared du, which will be easy to integrate since this will be the integral of a polynomial. Then, remembering that u is equal to tangent of x, we substitute that back in and have finished our problem. This problem initially doesn't look very much like the ones we've been talking about, but it does have an even positive whole number power for the secant, so let's split two factors of secant off and see where that takes us. The fourth power of something is the square of the something, so I'll be able to write secant to the fourth as the square of secant squared, but secant squared is 1 plus tangent squared, and now you see we'll be in business. We've got something that only involves tangent multiplied by secant squared x dx. We'll do a substitution with u equal tangent x. So du dx is secant squared x, du is secant squared x dx, and the integral turns into the integral of the square of 1 plus u squared over u to the 1/2 with respect to u, and then that integral is routine. We work it out in terms of u, and then to finish it, we remember that u is equal to tangent of x. The second recipe is if the power on the tangent is an odd positive whole number, we should split off a factor of secant tangent, convert everything else into secants, and then do a substitution. For example, the integral of tangent cubed x, secant cubed x dx is integral tangent squared secant squared tangent x secant x dx. The tangent obeys tangent squared equals secant squared minus 1, so this is going to allow us to do a substitution. The integral now involves only the secant, and down besides the dx, tangent x secant x, which is the derivative of secant x. So obviously, we'll be able to do a substitution on this one as well. We'll let u equal secant of x. Du dx is going to be tangent x secant x dx. My integral becomes integral of u squared minus 1 times u squared du, which will be easy to do since it's a polynomial. U squared minus 1 times u squared is u to the fourth minus 1 times u squared. Antiderivative is direct using our previous methods. Then we remember that u is secant of x, and we have our antiderivative. In this one, I don't have any explicit secant factors at all, but even so, 3 is a positive odd whole number, so I'm going to factor out tangent x secant x anyway. The power on the tangent is reduced to a 2, which will allow me to express it in terms of secant, and on the bottom of the fraction, I'll have the secant of x to cancel the one that I manufactured to write down at the end. This is integral fraction secant squared x minus 1 over secant x, tangent x secant x dx. Obviously, the substitution u equals secant x will turn that into the integral of u squared minus 1 over u du. U squared over u is u. 1 over u is, well, 1 over u. Antiderivative, 1/2 u squared minus natural log absolute value of u plus a constant. And then remember that u was just secant of x, and you're done. If you have an integral in which there are only even positive whole number powers of tangent, then the suggested strategy is to split off a tangent squared of x and convert that tangent squared of x into secant squared x minus 1, and then repeat as needed. For example, the integral of tangent to the fourth x dx is the integral of tangent squared x times tangent squared x. Split the second tangent squared into secant squared x minus 1. You'll have integral tangent squared x secant squared x minus tangent squared x dx. The integral of the first term is easy since secant squared is the derivative of tangent. Therefore, we'll just have to deal with that second term, tangent squared, but it follows the even whole number power of tangent pattern itself, so we'll do the same thing again. Leaving the first term alone, since we like it, I'll think about the tangent squared of x that's being subtracted away. Tangent squared of x is secant squared of x minus 1, and being careful about the plus and minus signs, I have to integrate tangent squared x secant squared x minus secant squared x minus is plus 1 with respect to x. As mentioned previously, the first term is easy. The second term has antiderivative tangent x. An antiderivative for 1 is x, and then add a constant of integration, and this is our answer. This is our indefinite integral. In the case where you have no tangent factors at all, but the power on the secant is an odd positive whole number, the suggested procedure is to use integration by parts. Now, we've already done the integral of secant cubed x dx, so we'll look at the integral of secant to the fifth instead. I'll split that into secant cubed times secant squared dx, calculate du, calculate v, and then I'm going to write down the integration by parts formula. This is going to turn fairly nasty here. So the integration by parts formula gives me secant cubed x tangent x minus integral of tangent x times 3 secant squared x tangent x dx. I have two factors of tangent of x. Tangent of x squared is secant squared minus 1, so I'm going to use that trig identity here. I can rearrange this. The integral of secant to the fifth is secant cubed tangent minus 3 integral secant to the fifth x dx plus 3 integral secant cubed x dx. This doesn't look very promising, except if I add 3 times the integral of secant to the fifth of x dx to both sides, I get them all together. We've reduced the power that we need to deal with from 5 to 3. Now I'm going to be mercenary and say, I remember when we did the integral of secant cubed when we were doing integration by parts, and just reuse that result. The integral of secant cubed worked out to be 1/2 multiplied by the quantity secant x tangent x plus natural log absolute value secant x plus tangent of x. So writing that horrific expression in, and then finally dividing both sides by 4, we get our answer. We now know how to do integrals involving cosines and sines and tangents and secants, at least under certain circumstances. In the next discussion, we're going to show how you can take some integrals that we don't know how to do, and with a substitution, turn them into these types of integrals, which we now have a bag of tricks to deal with. I hope everyone's having a good day. I'll talk to you again soon.
The shadow knows.